Chi-squared tests of homogeneity and association are applicable to different scenarios, but that really only affects the hypotheses and the conclusion. Everything else is the same. There are two main differences between what happens when you do a goodness of fit test and what happens when you do one of the other tests. The way you compute the expected counts will be a little bit different, and the way you compute the degrees of freedom will be different. Otherwise, there are a lot of similarities. All the conditions for inference are the same, the way you compute the test statistic is the same, and the p-value is still going to be computed as the area under the curve of the right tail of a chi-squared distribution where the test statistic is the bound. A test of homogeneity is useful if you want to compare the relative frequency distribution of a single variable across several populations. So for example, let's say if you want to compare the distribution of letter grades amongst introductory courses in French, Spanish, and German, you have one categorical variable, which is letter grade, and three populations, one for each of those languages, so a test of homogeneity would make sense there. Generally, this is how the hypotheses would be set up for a test of homogeneity. The null essentially says that the distribution is homogeneous, that the distribution of categories is the same across all populations. The alternative says that it's not homogeneous. Like it says toward the bottom, the test of homogeneity is identical to the test of association in a procedural sense, but the test of association is more common, so that's the one that we're going to focus on. Additionally, it's not uncommon to see a test of homogeneity rephrased as a test of association. In the case of the foreign language example, if you treat the language as a variable and then think of it as one giant population instead of three separate populations, then effectively you'd be rephrasing a test of homogeneity as a test of association. One big thing that I need to point out is that sometimes this is called a test of association, sometimes it's called a test of independence. Those two things are the same test. Like it says there, a test of association is used to determine if there's evidence of a relationship between two categorical variables, and generally that's what the hypotheses would look like. The null would be that there's no association between the variables, the alternative is that there's some kind of association between the variables. If the reference that you're using calls this sort of test a test of independence rather than a test of association, the hypotheses would be phrased more like they are on the bottom of the screen, where the null would be that the variables are independent of each other and the alternative would be that they're not. One big difference between the goodness of fit test and the other tests is that there is just more stuff with the other tests. With a goodness of fit test, it's a single variable and a single population, so you really only need one dimension to display the observed values, which is why you can do it in a single row. But with the test of association, you're going to have two dimensions because you have the two variables. So instead of having an observed row and an expected row, a test of association would have an observed table and an expected table. The parts that are in blue on this slide are the changes from the goodness of fit test. The way that you compute the expected counts involves the row totals and column totals that come from the observed table. Any cell that you pick in the expected table is in a specific row and a specific column, so you just use those row and column totals from the observed table to figure out the expected count. The degrees of freedom is slightly more complicated, but it really isn't anything crazy. It's the number of rows minus 1 multiplied by the number of columns minus 1. If there's anything to watch out for here, it's probably this, because it's tempting to still think of it as being the number of cells minus 1, but if you do it that way, you're going to get a value that's too large. In this example, our two variables are gender and least favorite color. I made up the numbers here so we'd have some nice round numbers, but they're actually pretty close to the values that were in a real study. The ratios and things, they're actually very close. The null hypothesis would be that there's no association between the two variables, so no association between gender and least favorite color. The alternative is that there is an association between gender and least favorite color. To compute the expected counts, the first thing that we need to do is add up the row totals and column totals in the observed count table. Add across to get the row totals, add down to get the column totals, and from there we can compute all the expected counts. The first one, the expected count of people who are male and whose least favorite color is orange. We have a male row total of 90, an orange column total of 55, and the overall total is 185. So the expected count would be 90 times 55 divided by 185, which rounded to two places is 26.76. Next, the expected number of people who are female and who have a least favorite color of orange. We have a female row total of 95, an orange column total of 55, overall total of 185, so 95 times 55 divided by 185, which is 28.24 rounded to two places. Then you do the exact same thing for every other cell in that table. Since there are 2 rows and 5 columns, we have to do this for 10 cells, and all that computation is in the lower 2/3 of this slide. Toward the top of this slide is a filled-in expected count or expected cell frequency table. Once we have that, we can use the observed table and the expected table to put the test statistic together. The test statistic is computed the same way it was before. It would be the sum over all cells of the observed count minus the expected count, quantity squared, divided by the expected count. So we're going to have 10 of those components this time because we have 10 cells in that table. The first one, male and orange, the observed count was 22, the expected count was 26.76, so that component, 22 minus 26.76 quantity squared divided by 26.76. The next one was female and orange, observed count of 33, expected count of 28.24, 33 minus 28.24 quantity squared divided by 28.24, and so forth. It's that procedure over and over again for all 10 cells, and then once all of the algebra is done, once this is simplified all the way down, we end up with a test statistic of 18.381. To compute the p-value, the first thing we need to do is get a value for the degrees of freedom. Since there are 2 rows and 5 columns, the degrees of freedom will be 2 minus 1 times 5 minus 1, which is 1 times 4, or just 4. So the p-value can be computed using a chi-squared distribution with 4 degrees of freedom. If you look in my screenshot, there's the degrees of freedom box on the right with a 4 in it, and it can be computed as the area under the curve of a right tail. So I have right tail selected in the upper left, and then the bound will be the test statistic of 18.381. We're getting a pretty small p-value of 0.001. The conclusion at the bottom, the p-value is less than the significance level, so the null hypothesis should be rejected, which means that there is sufficient evidence to conclude what's in the alternative. Here, that would be that there is an association between the two variables, gender and least favorite color.